Hello and welcome to this lecture. We are going to see one of the very important applications of operators, which is in linear systems. Now, linear systems dominate all of engineering, even circuit theory. In fact, when a few lectures ago you saw that there was this abstraction of a two-port network of a circuit, which was like a linear system, right? What do I mean by a linear system? Input is a vector here of length 2 and output also is a vector of length 2, and this linear system is a matrix 2 by 2, and the output becomes matrix times input. Now, it turns out in linear systems there is also something called a state, and the state is something that evolves over time, but the evolution is linear. Okay. So, here is the picture here. The state at time k is a vector of length 2. Okay. I am going to call it xk1, xk2, okay, because as k changes the state will change. How does it become the state at time k plus 1, which is xk plus 1 1, xk plus 1 2? There is a linear system here, the matrix A. So, xk plus 1, the vector xk plus 1 comma 1, xk plus 1 comma 2, the first coordinate and second coordinate at k plus 1 is the matrix A times the state at time k, which is xk. So, xk comma 1, xk comma 2. I hope this is clear to you. So, the state at time k plus 1 is the matrix A times the state at time k. Okay, so, this is a model that is used so frequently in control theory, in circuits, in engineering across the spectrum. Okay, maybe not 2 by 2, maybe you use a larger size, but 2 by 2 is a good place to start. Okay. So, what happens now is, here is the interesting question that leads ultimately to eigenvalues, eigenvectors and all that. How does xk depend on the initial state x0? This is an important question, right? So, usually your state is evolving, you have a system that maybe it's built with some devices and all that, and your states maybe are voltages and currents. I want to know what happens to xk as time evolves. For instance, I am very concerned if the state is going to blow up, because if the voltages and current become larger and larger, then I have an uncontrolled system. Okay, things may burn, right? So, things like that can happen. So, I do not want to allow for that. So, I really need to know how xk depends on the initial state. What if I set the initial state to something, what will happen to xk? Okay. So, let us look at that closely. Xk is going to be A times xk minus 1. Okay. It is the same rule as this. Instead of k plus 1 k and k plus 1, I put k minus 1 and k. Now, notice what happens here. Xk minus 1 now, I can write it as A times xk minus 2. But notice what happens here. You have A times xk minus 2. I know that that is the same as A square times xk minus 2. Okay. So, notice this xk is A times xk minus 1. By using the simple device, it became A squared times xk minus 2. Now, I can repeat this. It is the A squared times A times xk minus 3. That is the same as A cubed times xk minus 3. Right. Now, I can keep on repeating it. What will happen? I will get A power k times x naught. Okay. So, notice how in these linear systems, state evolution is controlled by the power of the operator. Okay. So, powers of a matrix plays a very crucial role in study of linear systems, and we should study what happens to a matrix when you keep raising it to higher and higher powers. Okay. So, let us look at it more carefully. So, operator and matrix powers, you have a linear operator T from R2 to R2, matrix M of T size 2 by 2. That is the corresponding matrix with respect to the canonical basis, let us say. So, V is xy in R2, T of V will become the coordinates of T of V. I mean, we always write it as equal, you know what it means, right? So, T of V, the coordinates of T of V are M of T times xy. That also belongs to R2, we know that for sure. So, now if you do T of V, so once you see that T of V is in R2, you can see that the composition of T with itself is possible. So, you can do T of V, you get T squared of V, and that the coordinates of it, I put equal to here, but hopefully you see that the coordinates of T square of V is M of T times M of T xy, which is M of T squared xy. Okay, so, this is how the matrix powers come and the operator powers come. So, you can think of also the operator powers. So, T square, T is represented by M of T, T square is represented by M of T square. You can repeat this again. T square of V is in R2, so you can put T of T square of V, which is T cube V, and that is represented by this vector, coordinates of this vector, and that is M of T cubed. Okay, so, you can continue like this, and T power n V is M of T, coordinates of that are M of T power n xy in R2. So, the linear operator T power n has matrix M of T power n. Okay, so this powers, the operator powers and the matrix powers sort of coincide for us. Okay, so how do we study this? How do we look at this more closely? That's where the notion of eigenvalues and all of that comes. Okay, so once again, to study this problem, we're going to take our traditional approach that we have always taken. First, we will consider easy cases. Okay, the cases where the matrix power or the operator power is very easy to describe, functionally as well as in theory, you can very easily write down. The two examples are scaling and rotation. Okay, it turns out for these two examples, one can very easily write down what will happen to the power of the matrix. Then we will start looking at some more general examples to pick up a pattern, and you will see that the pattern is seems to be more varied in the beginning. And then we will prepare some necessary background. You need some very basic matrix algebra, we will quickly see that. And then crucially, you need this notion of a complex vector space. So far we have been looking at only real vector spaces, meaning the scalars were real, right? And the coordinates of the vector were also real. So it turns out, to understand powers of a matrix, you need to move towards a complex vector space. Okay, so you have to allow for the coordinates to be complex numbers. You have to allow for the scalars to be complex. Okay, only then it becomes possible and interesting. And then this will enable us, surprisingly, to reduce the general problem to the easy cases. Okay, so this is where particularly scaling. Okay, so once we see that, we'll be able to study the powers of matrices. Okay, so let's pick that up in the next lecture. Thank you very much.